and Assalamualaikum. My name is Najwa Izzati and I will explain about the problem statement and objective for this project. For the problem statement, strong wind loads create the possibility of the collapse for tall buildings and structures like the Komtar building because of their vulnerability to the force of the wind. A strong wind velocity can have an effect on the convective heat transfer coefficient of the building. As a result, it causes an increase in the amount of energy that is used. For the objective, we have two objectives in this project. First is to investigate the effect of different wind velocity on drag force reaction toward the Komtar building using CFD analysis software. And second, to study how wind velocity and drag influence the heat transfer characteristic and overall thermal performance of Komtar building.
Hi, Assalamualaikum. My name is Cairo Hafiz. So, for the geometry of the model, our model is based on the complex Tun Abdul Razak, which is located in Georgetown, Penang. The model is shaped like a dodecagon polygon which have 12-sided. To achieve a vertical position, the Z-X plane was used for sketching. We also extruded the model to give it a 3D appearance, with the limit region area for this model is 200 meter by 120 meters. To accurately simulate the airflow around the Komtar building, we set a specific boundary conditions. For the inlet, we considered various wind velocity ranging from 1 meter per second to 42.7 meter per second, representing different wind scenarios. The inlet temperature was set to 300.15 Kelvin to match the ambient conditions. For the building front and back surfaces, we assign a temperature of 297.15 Kelvin to stimulate expected thermal conditions. These surfaces were modeled using steel, a commonly used construction material. By establishing these boundary conditions, we created a realistic simulation environment to analyze the interplay between airflow and the Komtar building. This enables us to gain insight into the drag force and the thermal behavior of the structure. With these carefully defined boundary conditions, we can now proceed with the simulation and make informed decisions regarding the design and performance optimization of the Komtar building.
Result: we collect data from 6 different wind conditions. The temperature gradient visualization shows moderate temperature variation across the building surfaces, indicating a balanced thermal environment. The velocity streamline reveal airflow pattern and turbulence around the building. Our drag force analysis showed that the front surfaces experience higher drag forces compared to the back surfaces. Additionally, the total heat transfer rate decreased as the wind velocity increased, indicating more efficient heat dissipation.
The animation shows the velocity streamline in yield condition, which is 18.9 meter per second. We can observe that the streamlines aligning themselves with the direction of the winds, emphasizing the strong and dominant flow direction. Additionally, the streamlines may exhibit patterns such as vertices or area of high and low velocity. By animating the velocity streamlines in yield condition, we can gain a deeper understanding of how the flow behave under the strong wind forces. This visualization helps us to identify uh, potential flow issues to optimize design and enhance performance and safety. For the benchmark, we're comparing between Burj Khalifa and our model. So Peter and the wind engineering team calculated that Burj Khalifa need to withstand up to 240 kilometers per hour, while our model just need around 188 kilometer per hour.
In conclusion, buildings' front surfaces experience greater drag than the building back surfaces due to increased resistance and flow separation. The thermal condition within the Komta building is steady and comfortable. As the wind velocity increase, heat transfer decrease, indicating faster convergence and of heat transfer rate.